So, in conclusion, we can write down the definition of isotopes based on what we have known so far. Isotopes are atoms of the same element, so it has to be of same element with different numbers of neutrons. Okay? Or we can also say that they have the same atomic number, but they have different mass numbers. Just like the 12th carbon and the 13th carbon. We have different mass numbers over here, but the atomic number has to be the same because the atomic number is the one that determines the element. Yeah. As long as the atomic number is 6, that is carbon atom. Yeah, just like if you have an element of atomic number of 2, then this for sure is helium. So the one that determines the atom is actually the atomic number. But of the same elements, you can have different numbers of neutrons or different numbers of mass or different mass numbers. Now, I will introduce you to yet a different terms that is called the atomic weight, or this is the same with relative atomic mass, symbolized as AR. To understand better the concept of atomic weight, or the AR for short, let's try to solve this problem. Okay. The chlorine present in PVC, so this is a polymer, has two isotopes, 35Cl with a mass of 34.97 AMU and 37Cl with a mass of 36.95 AMU. If the former, so this one, makes up 75.77% of the chlorine found in PVC, we are asked to determine the atomic weight of the chlorine, or the AR. Now, how do we solve this? You can pause the video if you want to try to solve this on your own first. Okay, now we know that in total, the isotopic abundance has to be 100%. Yeah. So if we have the 35Cl, 75.77%, of course the 37 one will be 100 minus 75.77%, which is 24.23%. Yeah, you can also try to calculate it in case I make mistakes with the calculation. Okay, so how do you determine the AR, or the atomic weight of an atom based on their isotopes? This is how we do it. So first, you take the isotopic abundance, so 75.77 times the weight of 35Cl, let me erase this, which is 34.97 AMU, and then you add this up with 24.23, of course, multiplied by the mass of this one, 37Cl, which is this one, yeah? 36.95. So this and that, and of course divide it always by 100. You can try to calculate this and you will end up with this value, 35.45 AMU. So, in conclusion, the atomic weight or the AR or the relative atomic weight or relative atomic mass is 4 Cl, chlorine, is 35.45. Don't forget, the unit is AMU. Now we will discuss ions. So if we know before that atoms, they are neutral, meaning that the number of the protons is the same with the number of electrons, ions is not neutral. They are charged. They could be, of course, positively charged. They could also be negatively charged. In this case, the number of protons is no longer equal to the numbers of the electrons. The one that is positively charged we call the cations, and the one that is negatively charged we call the anion. The one that is positively charged loses electrons. That's why it becomes positive, because it loses a particle that is, don't forget, electron is negatively charged. So when an atom loses an electron, for instance, then it will become positively charged and become a cation. On the other hand, an atom could also gains electron, and because electron is negatively charged, the atom will become now a negatively charged ion, or we can call it anion. So we have cation and we also have anion. Let's take a look at the example. We have, for instance, sodium, Na, from natrium. So sodium can become sodium plus while releasing one electron. And normally this occurs as gas, so in gas phase, in gas phase. Now, because the sodium loses one electron, the sodium itself now becomes a cation. Now it is a positively charged sodium. So if we call this an atom, this one is cation. On the other hand, we can also have, for instance, Cl. This can become Cl minus, but in this case, of course, they will, or this atom will gain an electron. So you draw or you write the electron not in this side, but on the other side. Also in gas phase. Okay? So now you have, instead of the neutral Cl atom, now we have an ion. So if this one is cation, because it is positively charged, this one is anion, because it is negatively charged. Now, of course, certain atom can lose the electron multiple times. For instance, magnesium, we can actually see them in nature as magnesium 2 plus. So in this case, you have two-step electron releases. So we have first Mg becoming Mg plus electron, and then the Mg plus will release another electron to result in Mg 2 plus. And this is actually very common in nature for us to see the magnesium cation, which is 2 plus in charged. The same also occurs for anion. Yeah? So you can also have more than just one gaining of electron. It can also be multiple charged anion. But in this case, it will highly depend on the type of the atom. Some atom will have the tendency to release only one electrons, like sodium. But for different atom like magnesium, the tendency is to release 2 electrons like this. Now, for this tendency, we will discuss in a different segment. Yeah, we will see all the tendencies based on the periodic table of elements. So based on this, we will take a look at the tendencies of different atoms to become either cations or become anion. Now you can also determine, for instance, you have magnesium and magnesium 2 plus, yeah, and then you compare to Na plus, for instance. You can determine the number of protons, number of electrons for each, because this is not gonna be the same. Yeah, I want you to try to determine each number for proton, for magnesium, for the cation magnesium 2 plus, and for sodium plus or Na plus. And in this case, of course, for the ions, you will see that the number of proton is not the same with number of electron. Now, while we are at this, there is another term that is called isoelectronic, meaning having the same number of electrons. So, for instance, you have X 2 plus and Y 3 plus. If they both have the same number of electron, for instance, I'm just gonna put any number that's on my mind right now, 7. If they have the exact same number of electron, then we call these two as isoelectronic pair.